Scientific theory versus scientific law. Words matter. Before we begin, let's set up our notes. In your table of contents, write scientific theory versus law and the page number it will be on. Then turn to that page. Measure 7 centimeters away from the left red line and draw a line from the top to the bottom at that 7 centimeter mark. At the top of the page, label it scientific theory versus scientific law. The term theory means a very different thing when used in everyday conversation and in science. In our day-to-day speech, we often use theory to mean a guess or unsubstantiated idea about how something works, as in, I have a theory that gremlins are hiding my car keys. In science, we would call such a guess a hypothesis, not a theory. A hypothesis is a proposed explanation for an observation. In this case, I am proposing that the explanation for why I can't find my car keys is that gremlins are hiding them. We're going to learn today what we mean by theory in science, as well as the word scientific law. A theory is subject to change as information becomes available. The ancient Greek philosophers whose ideas shaped the worldview of Western civilization leading up to the scientific revolution in the 16th century had a theory about why the planets moved across the sky. Aristotle believed that the planets and the sun orbited the Earth. He saw no sign that the Earth was in motion, no perpetual wind blew over the surface of the Earth, and a ball thrown straight up into the air doesn't land behind the thrower as Aristotle assumed it would, as if the Earth was moving. For Aristotle, this meant the Earth had to be stationary, and the planets, the sun, and the fixed dome of stars rotated around Earth. For nearly 1,000 years, Aristotle's view of a stationary Earth at the center of a revolving universe dominated natural philosophy, the name that the scholars of the time used for the studies of the physical world. In 1515, a Polish priest named Nicholas Copernicus proposed that the Earth was like a planet, like Venus or Saturn, and that all planets circled the sun. Afraid of criticism, many think Copernicus was concerned about the scientific shortcomings of his theories. He didn't publish his theory until 1543, shortly before his death. Scientific laws are typically conclusions based on repeated scientific experiments and observations over many years and which have become accepted universally within the scientific community. The law of superposition states that the rock layer is older than the one above it. So the relative age of the rock or fossil in the rock is older the farther down in the rock layers. Please pause the video and copy the following notes into your composition notebook. Scientific laws state what always happens. This can be very useful. It can let you predict what will happen under certain circumstances. For example, Newton's third law tells you that the harder you hit a softball with a bat, the faster and farther the ball will travel away from the bat. However, scientific laws have a basic limitation. They don't explain why things happen. That is why we have scientific theories. Scientific theories try to provide the most logical explanation about why things happen as they do. A theory might invoke dominant and recessive genes to explain how brown-haired parents ended up with a red-headed child, or use gravity to shed light on the parabolic trajectory of a baseball. Please pause the video and copy the notes into your composition notebook. A theory is constantly tested. If some data doesn't agree with the theory can be revised. If the theory cannot match the data, it's thrown out. That being said, sometimes a theory is well established and it has a lot of evidence to back it up. For example, we are looking at Copernicus's model on the left, and on the right, we have Kepler's model. Kepler took Copernicus's basic model and realized that the planets are not in complete perfect circles, but they go in eclipses. So a well-established theory is unlikely to be overthrown. It may just need to be modified a bit, such as you see here with Kepler. But science does not prove anything beyond a shadow of a doubt. In general, a scientific law is the description of an observed phenomenon. It doesn't explain why the phenomenon exists or what causes it. Laws are descriptions, often mathematical descriptions of natural phenomenon. For example, Newton's law of gravity or Mendel's law of independent assortment. These laws simply describe the observation, not why they work. Pause the video and copy the notes into your composition notebook. The law of gravity was discovered by Isaac Newton in the 17th century. This law mathematically describes how two different bodies in the universe interact with each other. However, Newton's law doesn't explain what gravity is or how it works. It wasn't until 3 centuries later, when Einstein developed the theory of relativity, that scientists began to understand what it is and why it works. Newton's law is useful to scientists in that astrophysicists can use this centuries-old law to land robots on Mars, but it doesn't explain why gravity works or what it is. For that, we need the theory of relativity. The theory of relativity explains gravity based on the way space can curve, or to put it more accurately, it associates the force of gravity with the changing geometry of space-time. Please pause the video and copy the notes into your composition notebook. One question I'm always asked is, how much proof does it take for a theory to graduate to being a law? Well, a house is made up of bricks, boards, nails, woods, doors, concrete, etc. A dictionary is made up of thousands of different words, and a symphony can easily have thousands of notes that all fit together in just the right way to produce pleasing music. In the same way, theories are based on a variety of scientific laws, facts, testing, and other evidence, all fit together in a way to offer an explanation as to how some part of the universe works. So just as houses don't become bricks, theories don't become law. Both are important, but they tell us different things. Law tells us what happens, and theories explain why something happens. But what if a theory turns out to be wrong? What if it has a flaw? Well, let's go back to the earlier example. What if you built a house and then realized there's a room with no door, no way to get in or out? Clearly, something needs to be done. Either decide the room isn't necessary and remove part of the building. The same is true for scientific theories. Finding one flaw in the theory of gravity would probably not send everyone back to construct an entirely new theory. Instead, scientists would examine the new evidence and see if there was a way to adjust the theory so that the new evidence fit. That happens quite frequently. As we learn more and more about the universe, we expand and refine our theories, our explanations of how the universe works. Occasionally, discoveries are made that are so profound that they do require that we discard the old theory. Then we start from scratch to develop a new theory that fits the new evidence as well as the old. Then the testing begins, with everyone looking for evidence that the new theory is wrong. Wrong? Isn't it meant to try and prove that it's wrong? No. It's not mean to try and prove it wrong. It's the way of science. In the words of a famous scientist, no amount of experimentation can ever prove me right, but a single experiment can prove me wrong. That would be Albert Einstein. And even after all these years, scientists are still performing tests to see if there are flaws in Einstein's theory of general and special relativity. Neither has been shown to be wrong, so they're still accepted and highly respected theories. The same is true for new explanations of how and why things work. After a great deal of testing and with enough solid evidence, often with much modification as more evidence is gathered, a new explanation may eventually be accepted for the exalted title of theory.